Good morning, students. Still enjoying this cool weather. So I guess I can wear long sleeve shirts that usually just collect dust in the closet. I don't know. I like the little change in weather, even though the sinuses always go a little bit crazy. I'll put up with it. I've gone ahead and I gave you an extra day on the homework and the quiz. I know some of you didn't need it, but some of you, I'm sure, were grateful to get it to give you some extra time. And then I sent the message out for the next test, which will occur at the beginning of the coming week. So those of you that are in the early college high school, of course, you'll have your time off from the high school setting, and hopefully this will just give you some time to focus on the math, and everybody just get some assessments out of the way before Thanksgiving. Unfortunately, the college continues, and so go ahead and do your planning and think about what you need to do so you can get your homework and you can get your testing out of the way, and then maybe take a day or so off just to relax with family and friends, or maybe just get some sleep. I think the nicest thing about having a little bit of time is that you have a more flexible time to rest and just relax without a lot of obligations to fulfill. So good luck as you continue to work on your mathematics. We're going to be done soon, so all that hard work will pay off. Now, what I want to do today is to discuss the hyperbolas. Like the ellipses, they have similar definitions. And then we want to look at translation problems where we actually have a situation where the origin of the coordinate system is translated based upon the actual algebra of the equations. And so that's a very important topic, and something you probably talked about maybe tangentially in other courses, but we'll discuss that today too. So let me go ahead and share my screen. Now, just like with the ellipse, we need a definition so we can move this into the territory of analytic geometry. So let's do that. And again, there's only going to be one word change here, so this is interesting. So our definition will just interchange one word. So we'll have a hyperbola is the set of points and let me get this cursor moved out of the way, set of points in the plane the difference, instead of the sum, the difference of whose distances from two fixed points is a positive constant. So, like I said before, when it comes to this definition, instead of the sum, we have the difference. Now, again, the hyperbola is a little bit different object, at least comparatively. The parabola, of course, corresponds to the quadratic function that we know a lot about. The ellipse is just a generalization of the circle, which we know a lot about from previous courses. But the hyperbola is something a little bit different. And again, this definition was based on what the actual Greeks did. Again, like I said before, the Greeks came up with all of this stuff from a very geometric point of view. And then, of course, the mathematicians of the 17th century, 16th and 17th century, and then forward, put all this into the algebraic realm. So So we, again, are enjoying all of the benefits of the conic sections that have always been around, but now the with the advent of the calculus, the conic sections provided really good examples, curves and things. When you do curve theory, it's great to have parameterizations of parabolas, ellipses, hyperbolas, all kinds of curves that are very useful for the study of the calculus. So I guess everything gets back to that word calculus, which I seem to say 5 or 6 times every lecture. So when we look at this, and I want to look at this just like we did the ellipse, the 2 fixed points will be done the same way. All of the notation will be the same, so we don't have to develop new letters. So that's going to make everything easy. So we're going to fix a C positive, and then we define the foci just like we did before. We'll have a focus 1, and these again will be distributed symmetrically about the origin just for convenience. So we'll have a negative C0, and we'll start with the x-axis, horizontal axis for the foci, just like we did for the ellipse. And then, of course, the positive constant will be done the same way. We'll fix A positive, and then we'll set 2A for the positive constant. Again, the number is somewhat arbitrary, like an integration constant in the calculus, and so we have flexibility about how we choose it. And we saw, at least from the ellipse, that this turns out to be a very useful selection for the positive constant. I mean, we do have that control with algebra, which is really kind of nice. And so now the subtle change here does make a big difference. Instead of a closed curve, we're actually going to get a curve that actually has 2 separate branches, and that really is interesting. So if we think about the structure with the x-axis and the y-axis, we can again locate foci. So this will be our second focus at C0. And then, of course, equidistant. So we'll have focus 1, negative C0. Now, one thing that's interesting here is that you can see that we could never have a point right here like the isosceles triangle, because that would make the difference equal to 0. So this is already starting to look kind of odd. I mean, we could possibly have maybe, you know, a point here, but it wouldn't be the case that we would cross or that we would have any kind of connected curve here. So that's the idea, thinking about the branches. So this is really different from the ellipse. So with that in mind, I'm going to take a point here, Pxy, and we're just going to apply the definition and see what it gives us. It's actually remarkable that one sign change will completely change the form of the curve that we get. So we'll look at this triangle, again, like we did yesterday, with an arbitrary point on the ellipse. Now, with that, we can look at this triangle and apply the triangle inequality, because again, like before, we need to get some connection between A and C if we're going to move the problem forward. So first, we will use triangle inequality. We'll just use the strict inequality, even though greater than or equal to is also valid. So we could say, for instance, if we said the distance between P and F1 plus the distance between the 2 foci, we'll write 2 equations. would clearly be greater than the distance between P and F2, thinking about sides of a triangle. And then, of course, we could just flip these around. We could say the distance from P to F2 plus the distance between the foci would be greater than the distance between P and F1. So those are just two simple equations there, and you're thinking, well, okay, so that's pretty clear. So what I want to do now is just isolate the distance between the two foci. And so we'll have distance P F2 minus distance P F1. And do the same for the second one. So the distance P F1 minus the distance P F2. Well, the idea here is that if we actually have a point on the hyperbola, one of these actual differences here will correspond to the constant 2a. So for instance, if it's true that this particular difference is positive, by definition of the hyperbola, this would equal 2a. And of course, the distance between the two foci is just 2c. Now, of course, maybe the flip is true. One of them has to be true if this point is on the hyperbola. So maybe it's this one. So this would be 2a by definition of the hyperbola. The difference of whose distances from two fixed points is a positive constant. And then, of course, the distance between the two foci is 2c. So in either case, so it's really without loss of generality, basically, we have 2c is greater than 2a, which is equivalent to c greater than a, which is the opposite of what we had for the ellipse. For the ellipse, we have a is greater than c. So at least now we're seeing that if this turns out to be an x-intercept, the curve will actually be interior to the focus, which again is already strikingly different from the ellipse. So these conic sections, though they seem fairly simple, get complicated quickly. Not in a very, very difficult way, but there's more to them than just some simple construction process. So now, if we look at this and say, okay, we'll just pick one. I mean, we know that these two equations here define the hyperbola. So without loss of generality, let's just start with the first one. So basically, we're looking at an absolute value, but it doesn't matter. One of these has to be true. So without loss of generality, let's just assume that the distance between P and F2 minus the distance between P and F1 is the positive constant. So again, slap the absolute values on, but either way, you just get a negative sign if it's less than 0. And then when you square, it's all absorbed anyway. So the beauty of algebra is that we have the theoretical disposition of the real numbers, which again is unique in and of itself, and is the basic set for doing analysis. Generalization of calculus is topology. And so if you ever take that, you'll continue with these ideas and make them even more abstract. So what I want to do is basically do what I did yesterday, is to isolate one of the distances and square, and then get it to the point to where we've simplified it as much as we can, and then substitute all the values like we did with the ellipse. I want you to be able to do this. This is good practice. And if you just leave this out, you lose all of the elegance of doing the algebra here. So this will be your second chance to get this right. So first, let's go ahead and move this over. So we'll have the distance between P and F2 will equal 2a. So very similar to the last one. And a lot of times I'll just say, oh, well, this is like the last one, everyone, so we don't have to do it. But I feel that the level of comfort is not there. So let's just go ahead and see what this will give us. Now notice here, if we isolate one of the distances, we can square and get rid of some of the radicals like we did in a symbolic way last time. So square. So this is going to give us the distance squared between P and F2. And now we'll just square the binomial. So we get 4a squared. And the whole time, I'll write this again over here. We'll keep reminding ourselves of this. We'll eventually need to use that. So this will be plus 4a times the distance between P and F1 using the inner term of the binomial expansion plus distance squared between P and F1. So just like yesterday, we're doing the symbolic computation here to minimize the amount of drudgery. Is enough as it is. Okay, so now we'll do the same thing we did before. Let's isolate this and put all the other riffraff on the other side. So we'll write this first and then take all these over, but I'll put this on the left-hand side. So this will be 4a times the distance between P and F1. And so we want these two terms to join this term. So this will be the square of the distance between P and F2 minus, if you like, let's just go ahead and write this term, or this one, it doesn't matter, 4a squared. And then minus the distance squared between P and F1. So again, let me just describe what I did here. We want to isolate, just like we did before, this term, which we know still has a radical in it because it's not squared. So I'll just write this over here on the left and then transpose these two terms. So I have the distance squared between P and F2 minus 4a squared, and then minus the distance squared between P and F1, just like we did before. Now this is the point where, okay, we've done enough symbolic computation so we can start filling everything in and then square one more time. So 4a, so we have the distance between P and F1. So here, P and F1, so this is going to be x minus a negative. So we get x plus c squared, and then y minus the 0, so that's just a y squared to the 1/2. Now that's going to be the same over here without the radical, but let's do this one. So this will be x minus c quantity squared, and then y minus 0. So that will be plus a y squared, okay? And then we have this term minus 4a squared. And then of course here, we'll do the same. We just get this, and of course I need my plus here. This will just be the minus of this without the radical. So we have minus x plus c quantity squared plus y squared. So that term over here without the radical, and let me move this up 1/2 a little bit so it looks like an exponent. It looks a little bit low. Okay, so now let's just see what we get. Let's reduce this. So we get a 4a, and if you like, go ahead and expand this, x squared plus 2xc plus c squared plus y squared to the 1/2, and go over here, do the same, x squared minus 2xc plus c squared plus y squared. Remember last time I just put the y squared on the end because I left it out, but I'll be sure to use it, leave it in this time, minus 4a squared. And now here, that's just what this is. So let's just run the negative through all of this. So minus x squared minus 2xc minus c squared minus y squared. So we expanded this over here, and so we'll just slap the negative on all of it. And so now we can see a lot of things absorb, the x squares, the y squares, the c squares, and we're just left with negative 4 copies of xc, so this guy and this guy. So this is negative 4xc, and then we have the minus 4a squared. So again, that takes care of everything. So we really did need to do this at this point to see the simplification. The symbolic will not give us the simplification. And so here we just have 4a x squared plus 2xc plus c squared plus y squared to the 1/2. So now let's get some extra paper here and continue the computation. So now what we can see is that just like we had before, the 4's will absorb. And so we can go ahead and square again. And let me do the, yesterday in calculus, we were talking about smooth curves. I said, let me smooth out the screen, focus. And I said, yeah, my sense of humor is lacking, but as my students in the past have said, it's a dry sense of humor. So I guess that's somewhat of a compliment. So now notice the 4's all absorb. So let's do that. So that's going to be an a x squared plus 2xc plus c squared plus y squared to the 1/2 equals a negative xc minus a squared. So now what we can do, if you like, is just go ahead and square both sides again. So square. Now, one thing that you notice about all of this is that when we look at what we have, it just mimics everything we've done before. So let's go ahead and square. So we'll get a squared times x squared. Square this, get rid of that, and then we get plus 2a squared xc plus a squared c squared plus a squared y squared. And now when we square over here, we get x squared c squared, and then plus 2a squared xc, because the product is positive, and hit it with a 2, plus a to the 4th. So let's see here. So this looks good. Excellent. Okay, so now notice we get some absorbing terms. So let's see here. These absorb. And then we want to get all of our x's together, all of our y's together, and the riffraff over here. So first, we'll have, at this point, we'll have a squared x squared, and then we'll subtract this, minus c squared x squared, and then we have plus a squared y squared, and then we want to take this over, and this will be, and so check that off. So this will be a to the 4th minus a squared c squared. So check, check. So everything's been taken care of. So now, of course, over here, we just want to factor. So we have x squared, a squared minus c squared plus a squared y squared. And then we have a squared times a squared minus c squared. But this is where we want to use c is greater than a. So of course, this would give us c squared is greater than a squared. So to kind of get rid of all these negatives, let's hit the equation with a negative sign to respect this inequality. So this will be x squared times c squared minus a squared minus a squared times y squared equals a squared times c squared minus a squared. So the negative here, we just flip to actually create the multiplication by negative. And now, of course, we can divide a squared, c squared minus a squared, c squared minus a squared, and then, of course, a squared, c squared minus a squared. So now, well, the hard part's over. I mean, the hard part was over once we set up the equation, because this is just busy work. So now we get x squared over a squared minus y squared over c squared minus a squared. And then, of course, we get a 1. So now you're thinking, okay, well, what are we going to do here? We'll do just what we did before. We will set b squared equal to this positive number, c squared minus a squared. So that will mean now that c squared equals a squared plus b squared. Before we had c squared equals a squared minus b squared. For the hyperbola, we had this. So they're just little subtle differences that we see between the ellipse and the hyperbola, but it's like how fascinating. The only difference is this, but it turns out to be a major difference. So this gives us x squared over a squared minus y squared over b squared equals 1. So what we see with this is that we do get branches, but we get an asymptotic behavior that we would not really expect. So we've got this here. We have the foci plus or minus c. And again, just like with the major axis for the ellipse, we're going to call the axis that contains the foci. For the hyperbola, this will be transverse axis. That'll take the place of major. But we don't really have the minor axis. Sometimes it's called the conjugate axis, but Dr. Stewart doesn't really highlight it. So this will have vertices just like before. It'll be let's say B1 negative A0, thinking of an x-intercept, so to speak, and B2, or plus or minus A to make it quick, A0. So with the hyperbola, we have basically what we have with the ellipse, though we don't focus on a minor axis. We have the foci and we have the vertices. Now, one thing that is somewhat interesting here is that we have an asymptotic deal going on, and that has to do with that difference bit. So what I want to do here is just kind of leave a little blank here, because we can't really say anything about what I want to speak about until I do some calculations. So when we think about the ellipse, or excuse me, the hyperbola, we're generating the same types of ideas that we did with the ellipse, but there's one big difference here. We're not going to have the concept of eccentricity. With the parabola, we had the concept of focal diameter. So now we're going to have an asymptotic concept that we have to deal with the hyperbola, and let me show you intuitively how that's going to work. So notice here we're going to look at this equation and just isolate the y squared over b squared. So y squared over b squared, just like take this over and take the 1 over. So this will be x squared over a squared minus 1. And so now if we get a common denominator here, we do this all the time. I mean, you all live to do algebra with trigonometry. The trigonometry makes you better at algebra, that's for sure, and arithmetic in general. So if we get a common denominator, we have this and just factor the a squared downstairs exterior to this. And then of course you can cross multiply by b squared. So now we see, just like before, the a, the b, and the c by definition are positive quantities. That's how we define these. We fixed a positive a, we fixed a positive c, and then we define b squared to be c squared minus a squared. That's a positive number. And then of course, b will just be like an intercept, though it's not part of the curve, it will help us to draw what we're gonna figure out that we get here. Now, at this point, these are real equations. So we have y squared equals this. And we're thinking, okay, well, we can use the square root property. So we've got what? If and only if y, again, we have the square root plus or minus the square root of b squared over a squared, which is the absolute value of b over a, but these are by definition positive. So we just get plus or minus b over a without having to worry about retaining the absolute value. And then we have the square root of x squared minus a squared. Now, what I want to note here, and then we can do this algebraically, is that the thing that's odd about this is that this gives you 2 branches of the hyperbola. And if we look at this, this only works when x is a or bigger. So when we think about here, we know now that the a, or the vertex 2, is going to be right here, 0a. So the curve starts here, but then the values of x move this way. So this curve is going to have to move that way. I mean, the algebra tells us what this curve has to look like. I mean, the Greeks invented the curve through construction, but we're now inventing it through algebra. So the domain is saying that we're going to have to go this way. And then, of course, if we have the other vertex over here, which is b1, negative a, 0, the same thing ensues. Nothing over here will make sense with the radical. We'll have a negative number. So then the curve will have to start here and start moving out this way, and even here by symmetry. So we're getting 2 separate branches, and right here is like the no man's land, like there's nothing. It's a void, like the Death Valley, so to speak. So this is extremely dissimilar from the ellipse with one change, difference. So if you tell your friends what you're studying, apprise them about what you're studying. Tell them what you're doing. Mathematics, we had a conversation yesterday that I always told my students at the conference hour that I took a lot of French, and so it always messed up my spelling. I've always done well in English, but I've always had to be very careful about spelling. And individuals will say, well, Professor Ron, you're well spoken. I said, well, that's because I've studied another language. But we have to look more deeply at what we do, as opposed to just saying, oh, we're just studying conic sections. You know, we have to think about this in a more esoteric manner, as opposed to just manipulating things through technology and having no deep understanding. So now we can see that the curves will have to move out this way, just because now when we look at this, the domain requires that. So that's why you learn how to compute domains. So the domain here is going to go A out to infinity, and then negative infinity to what? Negative a. So the thing that's interesting about this is that this gives you two branches, one going this way and one going that way, and then the negatives give you the ones that are reflections in the x-axis. So understanding this algebraically you can do. So then you think, so what are you trying to say, Professor Ron? Well, look at this. X is the only variable. So as X gets really large, this A squared here just kind of fades into oblivion. And so basically we just end up with something like this. And you're thinking, oh, that's really like the square root of X squared when X is positive, that's just X. So basically what's happening is that the curve is approaching the line B over A times X as X becomes arbitrarily large. That's a slant asymptote. And notice this is not a rational function. So this is not a slant asymptote to which we are accustomed. This is very different. So what we can say here is that consider the following. This is some intuitive calculus. So let's just set A to be bigger than, or excuse me, X to be bigger than A going out this way. And consider the following. That is, if we do the positive branch, B over A square root X squared minus A squared. And then we're going to say that the distance between this curve and this curve should be small as X gets large. If we're thinking intuitively that this will approximate this curve when X is really large, the distance between these two outputs should actually converge to zero in the terms of an intuitive limit. And we've been doing intuitive limits throughout this class. So don't hoo and haw at Professor Ron, this is calculus. No, this is intuition that you need to have before you take calculus. It's ridiculous how people say, oh, let's do some limits. No, let's think about them intuitively. Then you'll fill in the arithmetic when you get to calculus, if you decide to study and learn it. Or you can take the easy route and learn nothing and just get by, which I don't recommend. Now, let's go ahead and finish this. Let's just do some algebra here. Let's factor the B over A. So we're just going to say this means X is getting large. So we'll just leave it there for now and then intuitively figure out what's going to happen. So factor the B over A because it has no X in it. And now if we look at this and we think about this, we're going to have the square root of X squared minus A squared minus X. And here's the trick, everybody. You do the conjugate method. Just like we do with algebra and trig. We'll do the square root. This is to uncover what we already think's going on. Square root of X squared minus A squared plus X, the square root of X squared minus A squared plus X. And that's what we call, Professor Ron calls the convenient one. Why is it the convenient one? Because that is one where it's defined. And the idea is that we can actually transform what we're doing here to make what we think is going on more intuitively obvious. So now just think about the binomial here. So this gives us B over A, the limit, as X becomes large, just like we did with the horizontal asymptotes. And so notice here, we get the X squared minus A squared because the radicals absorb, but the outer and the inner absorb because this is a difference of two squares. So we get X squared minus A squared. And then of course here we just get minus X squared. So now we're thinking, well, this is what we have to do because we don't repeat conic sections in calculus unless you have time. So we've got to get everything we need to know at least about the basic conic sections in pre-cal. So now notice the x squared is absorbed and we just have a negative a, which we can just factor because it has no x dependence. So this gives us a negative a squared times b over a. And then we have the limit as x approaches infinity of, well, what's left? 1 over the square root of x squared minus a squared plus x. Now, again, this is just basic factoring that we do in pre-cal. That just turns out to be what? A negative a times b, because the a absorbs into the a squared limit. Now, of course, we can factor the x squared here and take the square root of it. It'll be positive. It'll just be x with no absolute value because x is bigger than a by hypothesis. So this will give us 1 over x times 1, and this will just give us 1 minus a divided by x quantity squared because we factored the x squared and that didn't have an x squared. And then, of course, the x gets factored here. So that's just plus a 1. So now intuitively, we look at this and say, okay, as x goes to infinity, this x gets really, really, really big. 1 is fixed. So this gets close to 0 from above. As x gets larger and larger, this gets close to 0. And then this just converges to 1/2 because again, the 0, the x, a over x, as x gets large becomes really close to 0. So we end up with the square root of 1 plus 1. So this is basically 0 times 1 over 2. And 0 times 1 over 2 is 0. So basically what we've shown here, and then of course, all you have to do in calculus is fill in a couple of limit theorems, but the intuition that you do when you look at limits at infinity is basically what you've learned when you did horizontal asymptotes for rational functions. So I'm just taking what we've done already with the like thinking ratio of leading coefficients. Now we don't have any coefficient up here. It's just a 1 and the x gets really large. So there's no hope for this except to converge to 0. And the same here to 1/2. So in the limit, we do see that these functions converge. That is, the branch of the hyperbola converges to this line b over ax. And so this means, or this implies, that we get slant asymptotes or oblique asymptotes. So what's neat about this is that this is really what we've been doing all along, but it's disguised. It's disguised. Until we just actually look at this branch, we don't think slant asymptote because we don't have a ratio of polynomials like we're accustomed to. So we get slant asymptotes for this branch, and then of course the branch on the other side of the y-axis. So we have y equals plus or minus b over ax, if that is not amazing. So the thing is, and you're like, okay, well, Professor Ron, how do we take all of this and get a picture? Let me show you. And the nice thing is that we don't have to graph these lines in the old-fashioned way. We can be extremely, extremely lazy. So let's just go ahead and remind ourselves. Let's do, so for instance, I can do the general picture here. Let's just do a general picture of this. And then it's the recipe to do any example. So for instance, we can think of our vertex 2, a0, and then vertex 1, negative a0. And then, of course, we'll have the y-intercepts, b and negative b. So we've got what, x squared over a squared minus y squared over b squared equals 1. And so what we can do is we can create a little box from the a's and the b's. And this will actually give us the slopes of those lines b over a. So when you find your a and your b from your equation, you can make your little rectangle here and then draw in the diagonals of this rectangle and extend them. So this gives you your lines without having to plot them in the old-fashioned way. You plot the points on the lines. These are clearly points on the lines right here, but you're not liking, oh, okay, there's a point, there's a point. You write your intercepts and then you construct the points by constructing the rectangle, which you kind of get for free. Because you did all this work here, you might as well use it. Do the same here. So now what we see here is this is y equals negative b over ax, and this is y equals positive b over ax, the positive slope. And now there's your point on the ellipse here for the branch we were talking about. Like I said before, the curve has to move this way. It can't move interior where there's no domain. So we use this asymptote to draw the branch like this. So we can get our branch, one branch. So here's the positive radical. Here's part of the negative radical. And then we do the symmetry here about the box. So what we're seeing in this case is that the construction of the asymptotes, just like we did with the rational functions, help us to sketch the graph. So this is just a reasonable facsimile of what's going on. The asymptotes just act as guides, just like the vertical and horizontal, they act as guides so you can sketch. So now the positive radical is comprised of these two branches here. The negative radical, these two branches. So here's a function right here that goes here and here. That's that square root function we just dealt with right here, this one. And then of course the negative one is this branch and this branch. So you get a disconnected graph. So the idea is that you work on this just like you do the ellipse. You get the standard form, except now you've got a minus instead of a plus, and you find your A and your B, and then of course the foci will be exterior. The foci are going to be exterior. So you can just graph this. F2 will be C0. F1 will be negative C0. And so we'll say the transverse axis has length 2a. That's what we call the transverse that contains the foci, but we go from, the a to the negative a. And so with this type of construction, it's like doing an ellipse, but you do an additional step. Instead of doing the eccentricity, you just write these and draw your box and dot in your diagonals. Now, of course, we can say, well, Professor Ron, what about what we did with the ellipse? Does it matter? Could we have just put the foci on the y-axis? Absolutely. So if you switch, we get the same deal, just like we have with the ellipse. So we can switch x and y. So this would mean foci on vertical axis or y-axis. So now when we switch, we'll get y squared over a squared minus x squared over b squared. So basically, when we think about this, the positive term, one without the negative, will always give us the intercept. So now we'll have y-intercepts, so the branches are going to be going like this, okay? And so basically, that's all we have to do. I mean, everything else is the same. C squared equals a squared plus b squared. And now the foci are on the y-axis. So we say z, I'll do the shorthand, plus or minus c. And then the vertices will be on the vertical axis or y-axis. We have plus or minus a, okay? Just like we did before with the ellipse. And now the x's and the y's flip. So we get x equals plus or minus b over a y. And then, of course, if you just solve for y, to do it like because we're lazy, we like to solve for y, we get y is plus or minus a over bx. So now the idea is that the intercepts along the y-axis will be the a's, and then along the x-axis, you'll have the b's. So when you do rise over run, you get a over b. So this is really important. I mean, you know this now, but we get this all for free, but we can't just be careless. So when we switch the x and the y, and it turns out that the negative is associated with the x, so that we have y-intercepts instead, the asymptotes flip from b over ax to a over bx. But just remember, this is always associated with the intercept axis, just like the larger denominator for the ellipse is always associated with the major axis. So we get the same setup here. Everything's good. Everything's nice and simple. So again, all you have to do with these curves is basically do your little note card like we did with the trig identities, where you kind of just wash yourself with all these little attributes that we have for these curves. So for instance, let's just go ahead and draw the curve when we have this equation. So we'll just get a general curve for this. So now we have the A, so we'll just say vertex 2 is 0A, vertex 1 is 0, negative a, and then we can go ahead and put in the foci. We know where they live now, exterior to the curve. So we have F1, 0, negative c. And then, of course, you can put in your b's. And then draw your box from the a's and the b's. Again, this is not Rembrandt. It's just to give you a nice rendering that is reasonable. We can't draw a graph. We can't draw infinitely many points. We just draw a picture of the graph. And so now you go ahead and draw in your diagonals. You know you're in a math class when everything runs together. You draw a picture and you have to, but it's all good. It's all related, right? So now we get y equals a over bx and y equals negative a over bx. That didn't come out too good. Let me rewrite the a over bx. And so now you have your a, your intercept here, but the branch runs this way. So it really kind of gives you, a step up to do these. If someone gives you an asymptote and then gives you a point, you know what kind of hyperbola it is. when you measure where the point is relative to the asymptote, because you can't cross the asymptote. You can't cross this slant asymptote. So that really tells you what kind of curve. It'll say you either have this one or that one. And so here's same thing. Now what we see is that the branches here, this branch, the positive branch, so to speak, is continuous. Here the positive branch exists of two pieces. The negative branch exists of two pieces. Here they're connected. So it's really different. When you switch the x and the y, that's a bona fide function right there. That one is too. Here you have to kind of cover up here. That piece and that piece is a function. This piece and this piece is a function. Where these are discontinuous, these branches are continuous. So just flipping the x and the y give you really different looking branches that we didn't basically have with the parabola and the ellipse. So when it comes to doing the hyperbolas, we have the additional construction of the asymptotes that we don't have with the ellipse. So it's kind of like the asymptotes take the place of the eccentricity with the ellipse, but though it's more work. And the asymptotes take the place of the focal diameter with the parabola. So we're seeing that the hyperbolas and the parabolas are similar amounts of work because you've got this other line that's kind of entering into the deal. You've got the directrix. And with the hyperbolas, you have the asymptotes, neither of which you have with the ellipse. So the ellipse is circle, we think easier, less stress, true. Now let's look at just one simple example of this. So if we have some user-friendly curves. So for instance, we have a setup here where we know exactly what to do with these. So if we have a very user-friendly curve, let me just give you a user-friendly curve, just so you'll get used to the asymptotes. Say we have x squared, and we've got 16 minus y squared. I'll give you some perfect squares here just to give you a nice user-friendly example. Even though WebAssign gives you everything, if you've got a nice friendly example, just like doing trig equations, you just have to go out on the deep end sometimes and use identities that you don't want to use because you don't like them, because you don't know much about them, because you don't use them. So same thing here. So when we look at this, we'll say, what is this? Well, this is already in the nice form. We didn't have to divide to make the one. We've got the x squared term, we've got the a squared, the b squared, the y squared term. So this is a hyperbola, and it's not, I mean, it's a good one. What do they call the, there's a term, and I'll come up with it. You get the degenerate case when you just get a point, and that sometimes happens, but that won't be the case here. We didn't have to complete the square or anything. So when we look at this, we're thinking, okay, well, a squared is equal to 16, b squared is equal to 9. So c squared equals a squared plus b squared. I wanted to give you a nice Pythagorean triple here. So this will give you 16 plus 9, which is 25. So now we have c is equal to the square root of 25, which is 5. Now, of course, we have a equals 4 and b equals 3. Of course, most of the times we get square roots because, you know, we don't have perfect squares. So when we look at this, we're thinking, okay, well, we're good to go. This will give us vertices. I'll just do the shorthand now, and then I'll separate them when we plot them. This will be, in this case, plus or minus 4, comma 0. The foci will be plus or minus 5, comma 0. And now we have y equals plus or minus b over ax. So what does that give us? Y, so we have b over a plus or minus 3/4 x for the asymptotes. So again, how much work you have to do just depends on how complicated the original equation is. But that's just water under the bridge. If you have to do more work, you have to do more work. So this is just a way to make real all of the abstraction that we did in the previous exercises. So now, and of course, once we do this, when you do the ellipse, you can think, okay, well, you would say transverse length. So we think about the transverse axis length is 2a. So that will be 2 times a 4 or 8. So that's just a simple calculation like you have with the ellipse. Nothing difficult there. And so now you can say, all right, well, we can get a nice simple picture of this. And then, of course, you can use all the attributes of the hyperbola to answer questions like we've done. Very simple. You're good with that now. I mean, now you see the drift. So we think again like the ellipse. If it's not translated, the center is 0, 0. We're thinking the center here as being 0, 0. Also, even though we don't have a vertex like we do a parabola, we think that being the center of the hyperbola, which will be kind of like the quasi-center of the box. So now we have what? 4. So we can mark that off. So 1, 2, 3, 4. And here 1, 2, 3, 4. Again, no Rembrandt, just basic. And then of course the 3, 1, 2, 3. And same here, 1, 2, 3. So we can draw our box. You don't have to really plot any points so much, except if you want to plot the vertices. So we could say vertex 2 is 5, 0. Vertex 1, -5, 0, right there. And then draw the box created from the A's and the B's. And so you can just dot them in. So the graph is simple. I mean, the graph is just kind of the gravy. Okay, it's just the gravy. The hard part is getting this stuff, and unless we're translating or rotating, it's not very difficult. So now we can say, okay, so we can draw the curve with the x-intercept here. Same on this side. So you get these nice, again, here's a curve, here's a function here, and here's the function here. And then if you like, you can label here, y equals 3/4 x, and then y equals -3/4 x. So again, you see that these curves become infinitely large, but you know they're restrained, so to speak, not like the exponential function. So again, you could be doing a calculus problem or differential geometry and a little ant, and you're walking along this branch of the hyperbola, and we would work out a way to parameterize that. So you could just do your little kinematic problem in physics, driving along the branch of a hyperbola. So the key here is just like we do with the parabola and the ellipse, we look for a standard form, and then from the standard form, we can move forward. Remember now, C is bigger than A, so instead of C squared equals A squared minus B squared, we have C squared equals A squared plus B squared. So the hyperbola only offers additional work like the parabola does with the asymptotes, directrix type deal. That's it. So very straightforward. Now, I want to say something about another aspect that we contend with when it comes to doing conic sections. And this has to do with translation. So often when we work a problem, it might be the case that we have extra items. Like for instance, if you have a quadratic equation that you're completing the square, you might, in addition to an x squared term, you might have a 3x term. And so when you solve by completing the square, you got additional work. You know it's quadratic. It's just you got to work a little bit harder. Okay. When you can just use the square root property, there's less work. So we have the same concept that ensues with any curve, just like function transformations. We move functions around using the transformations. So it stands to reason that we can actually take a curve and move the origin around. So this is what we're going to call translation of axes. Translation of axes. So the idea is that how will we, unless we just make the translation, how will we uncover it? So for instance, let's just say that you had the following hyperbola. I'll start with a hyperbola, but we'll do a parabola example. That'll be a little bit easier. But just for instance, say we start with this. We've got just the last problem that we did, 25 minus y squared, and then we had, I think we had the 9, right? Was that a, let me check here.
That's correct, sir.
I think it was a 16. Let's see. Yeah, it's a 16. So it's a 16. Yeah, that's why I keep all my papers, but I don't keep them in order, do I? So we have equals 1. And so say, for instance, we were thinking of a translated system. So maybe we have a new origin. We're going to call it O prime, which will be our new origin, but it's going to correspond to, say, the numbers, numbers h and k. So we'll say something like this. Let's see, I guess I can use, I'll just use the point Q, and I'll just say HK. So we take a point in our XY coordinate system. So this will be the XY coordinate system. And we're thinking of this being our new origin. So this would imply that, and then of course, this is called the X prime, Y prime coordinate system. We have to, they're not derivatives, but I have to give it another name, and that's the easiest. Would say that the X prime would now be X minus H, and the Y prime would now be Y minus K, thinking about function transformations that we've done in college algebra. Or equivalently, we could say solve for x, x is equal to x prime plus h, and y is equal to y prime plus k. And we would call these the translation equations. So thinking about that, we're like, okay, we'll say this is our new point in our old system. So we're thinking we got something like this. So I'll draw a picture of what I mean, just to give you a visual. So we've got our XY coordinate system. And say over here, we have the point Q, HK. So this, I'm gonna kind of draw it away. This is like Q, HK. And that's where we're going to put our new system. And so I'm going to draw new axes. We're going to do what we call translate the axes. So this will be X prime, Y prime, the X prime, Y prime coordinate system. And then that's what we call 0 prime. And in this case, this would be coordinates in the new system. So this would be the 0 prime and the 0 prime as a number. And then down here, we get 0 for the origin and just the regular 0, 0. So when we think about translating a system, we think, okay, well, if we want to look at the new coordinate system, in the old, we replace X prime with X minus H. But if we've got the old coordinate system we want to express in the new, then we replace X with X prime plus H and Y with Y prime plus K. So what if, so we think about doing that. Okay, so that would be how we would translate if we wanted to move things that way. So that's the first case. So think of a situation where we actually had something translated, but it was disguised. And let me give you this example. So with that in mind, keep all this in mind, look at the following example. So we have 49 x squared minus 16 y squared minus 96y equals 928. So you're thinking, if these are the simple equations that take us from one coordinate system to the other just by function transformation, we should be able to figure out when we have one. So now if we look at this, we think, well, this is just in the old coordinate system, it's not translated. That's easy. Here, it looks like we've got something that looks like a parabola. We've got an x squared term and a y squared term with a minus, but we have some riffraff over here. So now what we want to try to do is maybe complete the square in y. It's already completed in x. See if we can uncover a translation. So now let's do this. So first, we're going to have 49 times the x squared. And here we'll have minus, so we've got a 16 in both of these. So this is a 16, and we have the y squared, and then of course that's a 6 here, so we have plus a 6y equals 928. So we look at this and say, okay, we think this is a hyperbola. Maybe it's degenerate. So we think hyperbola. And then when you look at this, you're thinking, okay, well, I need to complete the square here. So let's complete the square. So this is easy. This is just 49 x minus 0. So that's really not going anywhere. But we need to make sure that we see that. So that's x squared is just x minus 0 quantity squared. And then here we say we got the 16. And so now we've got what? Y squared, let's complete, plus 6y, and then half of the 6 is 3, square it, we get a 9. So we add a 9 and we subtract a 9. So basically, if we add the 9 to complete the square, we have to pay for it. So now what does this give us? Well, this gives us 49 times x minus 0 quantity squared. And now we have a minus 16. And notice here, this is just going to be a y plus a 3 quantity squared. But then we have a negative 16 times a negative 9, which is a positive 16 times 9. So that was kind of the additional, the product of waging war on this problem. We get stuck with that. And so now let's just see what this gives us. So this gives us 49 times x minus 0 squared minus 16 times y plus 3 quantity squared equals 928. Now, when we look at this, this is just going to be what? That's going to be a 4 and a 5, so that's a 144. That's a, well, that's a perfect square. So when we subtract, what do we get? We get a 4, and then we get what? We get an 8, and then a 784. Now, that doesn't look like a horrible number. We can try to break it down. So we have 784. Let's divide by 4. So that's going to be a 1, a 38. So here we've got, let's see, a 38. So that's a 9 and a 24. So that's a 6. Got another 4 in that. So that's a 4. So we get a 4 and then a 36. Oh, well, joy. That's a perfect square too. So this is just what? 4 squared times 49, or 16 times 49. So that's good, because look what we have over here. So now we're thinking, well, we've got translation. So let's divide. We want to get a 1. So we've got 49 over x minus 0 quantity squared divided by 16 times 49. Do all this symbolically and you don't mess it up. 16 y plus 3 quantity squared, 16 times 49. And then, of course, over here, we just divide it by itself, we get a 1. So now we have the 49's absorbed. We have x minus 0 squared divided by 16 minus y plus 3 squared divided by 49 equals 1. So now when we look at this and say, okay, well, we've got a minus, we can write this as a minus -3, but we have a translation that's occurred. So when we go up here, we see that we've got this setup going on. So here we've got an x minus a 0. So we've got x prime equals x minus a 0. So we could say h equals 0 if you like here. And then we have y prime, again using this equation, which is y minus a -3. So k equals -3. So now what we see is that the new origin, that is, now we've got what? O prime 0, 0 is just now in the original, and this is where I say, I guess you know what, let me use center. That way that a little bit simpler. We can say now the new center of our translated coordinate system will be the center from the old one, which will be 0, -3. So the translation equations say that now this particular hyperbola has a center at this point. So now we see that the Q here is 0, -3 in the old system, but it's 0, 0 in the new system. So again, the red system now has the new center 0, -3. So that's what I mean by translation. Now we're not going to have a hyperbola that's centered here. It's going to be centered at this number. So now let's finish it. So that's what I mean by translation. So basically, what is it? How do we get the translation? We simply just what? We just do what? We complete the square. So now, if you like, so we've got our C prime. Let's write the other stuff. Now that we want to get the focus and the new vertices and the new asymptotes, let's go ahead and write down what A and B are. So we have A squared equals 16. B squared equals 49. Remember, A is always associated with the positive term. So this implies, well, if and only if C squared equals 16 plus 49 and that'll be a 5, 65. So now we have A equals 4, B equals 7, and C, well, sorry, square root 65. It's close to 64. That's not half bad. So now we can do all of this. So now F prime would be, in this case, plus or minus square root 65, 0. And then we want to write it in the old coordinate system. So in that case, again, this is where we go back. This is the old coordinate system, and now we need the new. So basically, we have to add h and k to get the x and the y. So h is 0, so that doesn't change, plus or minus 65. You can write plus 0 if you like. And then for the 0 here, we just have 0, and we add the k, which is plus a negative 3, so minus 3. So now we get new foci, plus or minus 65 square root negative 3. Now again, so this is what you have to think of. We got x equals x prime plus h, and y equals y prime plus k. So this is x prime plus 0, and this is y prime minus 3. Remember, we started with x prime equals, in this case, x minus 0, and y prime equals, in this case, y minus 3, or plus a 3, minus a negative. So these are equivalent. So now the vertices, what are the vertices? Plus or minus a, so plus or minus 4, comma 0. Now let's move them to the new one. So we use this, so we just say plus or minus 4 plus 0, and then 0, what? In this case, minus a 3. So this gives us our new vertices. Sorry, I'm writing the F again. So we get B plus or minus 4, negative 3. And now for the y prime, we know we have y prime is b over a. So we have 7 over 4 plus or minus 7 over 4 x. So we replace, we just go over here, y prime, that's going to be a y plus a 3 equals plus or minus 7 over 4. And then of course, x is x minus 0, so that just stays the same. So if and only if y is equal to plus or minus 7/4 x minus 3. So when you do the translation, you basically have to go into your new coordinate system and then say, well, what did these look like in the old coordinate system? Because everything got flipped around. Because now this is the x prime and that's the y prime, like we have up here. And so if you want to graph it in the old coordinate system, here, this one here, and not the red one, then we have to make the translation that we do here. So what most students do, and this kind of makes it easy, when you say h is equal to 0 and k is equal to negative 3, they just say, well, you just need to add those to your foci and your vertices. And then, of course, in the equations, you replace x prime with x minus h, and you replace y prime with y minus k. But in this case, it would be plus because it's minus a negative. So here we have y plus 3. So again, the same translation process is what you did when you did your function transformations in college algebra. So what we're seeing here is that when we have what looks like a hyperbola, we set out to complete the square. And then we notice the translation here. We see, okay, h is 0, k is negative 3. So we can think of in general that we have a situation like this. we can think of x minus h quantity squared over a squared minus y minus k quantity squared over b squared equals 1, which is what we got here. So this would be the goal. And once you have the goal, then you have your translation equations that you can do to change these so you could actually plot them. But again, you can think, well, WebAssign going to want you to write these in the old coordinate system, unfortunately. So you have to be able to do this. But then the graph is really easy. So now when we think about the graph, we think of our new center here. Let me just write it, 0, -3. So let's go ahead and plot it. We just move everything based on these new numbers. Now notice here, if you want, you can go ahead and spread these out. So this will be a B2 will be 4, -3. B1 is -4, -3. And then here we can say, so I'll put a boxes around these. And then we could say F1 is square root 65, -3. Or F2, excuse me, the positive one, and F1 will be negative square root 65, -3. Put a box around that. And then for the asymptotes, we get 2. We'll just have 7/4 x minus 3 and -7/4 x minus 3, which we can just label. So now we can show 0, -3. So 0, 1, 2, 3. There's the new center of our coordinate system. So now we can just kind of be cheap. We can go over 4. So 1, 2, 3, 4, and get our B2 vertex right there, and then go over 4. 1, 2, 3, 4, and get this one. There's our B1 vertex. And then the B is 7. So 1, 2, 3, 4, or excuse me, 1, 2, 3, 4, 5, 6, 7. And then 1, so 0, 1, 2, 3, 4, 5, 6, 7. So draw your box. Right there. I should have given a little bit more room. I spread this out a lot. So now you can draw your asymptotes. Oh, this make some ink. We're running out of space. So when you draw it, so this is kind of the icing on the cake part. And then of course we've got here y equals 7/4 x minus 3. And here we have y equals -7/4 x minus 3. And then you can label your vertices. So this will be B2, 4, -3, B1, -4, -3. And then square root 65, that's going to be a round to 8. So 1, 2, 3, 4, 5, 6, 7, 8, about right here. And then see 1, so let's see, 8. So in this case, about 8, 1, 2, 3, 4, 5, 6, 7, 8, about right here. This is, again, you don't normally have to plot these, you just have to state them, but I'll just plot them. So F2, square root 65, -3, and F1, negative square root 65, -3. So this part is just, I mean, once you do all this labeling in your WebAssign, you don't have to worry about maybe plotting all of this, you know, when you draw it out, like when you do a test. The WebAssign will just basically say, list all of these and follow the formatting. And then they'll say, choose a graph. And that'll be the easy part. But the labeling here just kind of lets you know that the foci are exterior to the curve. And then you get your asymptotes by just drawing your box. Now, one thing that's interesting here is we can do the same for all the other curves. Now, I did the hyperbola first because it's the most complicated because you've got the asymptotes, but the other ones are not really as tough. So let's do a parabola. And then next time we'll do an ellipse. We have time. We'll just see how long this one takes. So now, let's look at a translated parabola. So here, example. So we've got, in this case, what we might think is a parabola. So we have x squared plus 6x minus 20y plus 29 equals 0. And we remind ourselves, x prime equals x minus h, y prime equals x minus k. Equivalently, x equals x prime plus h, y equals y prime plus k. These are the translation equations, and we must respect them. It's just like the arithmetic of the unit circle. You don't guess, you follow the translations. So now we think, because we only have a square term in x, we think this is a parabola. So let me refocus. We think this is a parabola. So we're gonna complete the square and see what we get. See if we get a translation of axes. So now notice here we can retire the y stuff and things, whatever constants, whatever, to one side, but we can complete in the x. So we'll have x squared plus 6x, leave some room here, and then we'll just say we'll have a 20y minus a 29 for now. Just retire everything to the right-hand side here. And then we're thinking, okay, well, this is monic, so we don't have to worry about that. So we're going to take half of 6 and get a 3 and square it. So plus 9 minus 9. So this will give us an x plus 3 quantity squared. And this gives us a 20y minus 29 plus a 9. So this is a 20y. This is a lot easier than the hyperbola. That's why I started with that. I just did hyperbolas, and then I thought, well, I'll just go ahead and translate that, get that out of the way. And so now we have x plus 3 squared equals 20 times y minus 1. So now when you look at this, we have the h is -3. We've got minus the negative. So this gives us the so-called new center. So we have the center in the old coordinate system, which would be -3 and a 1. So now when we go up here, we get x prime equals x, in this case, plus minus a negative plus 3, y prime equals, ding. The math always keeps us on track. That's a y. So we get a y minus a 1. Equivalently, we have x prime x with no prime equals x prime minus 3, and y equals y prime plus a 1. So those are the equivalent translation equations. So now we're thinking, wow, we're good to go. And then we don't have the a and the b. We just have, let me just remind you, we have what now? We have the x minus the h quantity squared equals 4p y minus k. So that's the translated equation. So now notice we have what? Here, 4p equals 20 if and only if p equals 5. So now let's just say here, the old vertex, we had the old vertex was 0, 0 in the old coordinates, or the new coordinates, and we want to move them to the old, which will be negative 3, 1. So here, when we look here, what do? We add negative 3 and we add 1 to the 0, 0. So this gives us V, or the new center, negative 3, 1. So there's the new vertex right there. And then the focus, remember the focus, I'm not going to put primes on these. I guess I should, but they're just specific numbers, so we'll live with that. And so now with the focus, we have 0, 5 or 0p. And so now we have to add the numbers. So this is going to give us focus 0 plus a negative 3, and then a 1 plus a 5. So this gives us focus negative 3, 6. And now the old, or in the new system, we have y prime equals the additive inverse of p. So we go to y prime and we get y minus 1 equals the negative of 5. If and only if adding 1, we get y equals what? Negative 4. So here's what we're doing to keep sane here. If we wrote everything in the new coordinate system, then everything would be just like we did in the first section on parabolas. But the key here is to be able to translate this into the old system so we know where things are. So the translation, though it's not trivial, we just want to be able to write this like we're still in the old system, but we've moved things around. So the translation can be obtained from the translation equations here. So this is really what you should write down every time you have a translation, and then fill them in and use them as you need, so you don't have to guess. If you start guessing, you will get it wrong. You always follow this. You do how I teach you, okay? Students always flounder with this because they don't pay attention to the translation equation. So once you've completed the square, that gives you the h and the k, which you can fill in and use here as you need. So now we're good to go. Let's just go ahead and get a picture of this. So we've got what? A negative 3, 1. And draw everything in. And then we can use our focal diameter if you want. So notice here, 4p, wow. So much for the scale. I don't think we'll worry about this. This is just going to be what? The absolute value of 20, which is 20. So I don't think I'm going to, half of that's 10, but we'll see. I don't want to draw points all day long. So let's just say here we've got negative 3, 1. So about right here. So negative 3, 1. So there's our vertex. And then, if you will, our focus is negative 3, 6. So 1, 2, 3. So we've got 1, 2, 3, 4, 5, 6. So we can go 10 in either direction. So 1, 2, 3, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So there's another point. So that's just a -3 plus a 10, which gives us a 7. So this will be 7 comma 6. And do the same over here. So a -3 and a 10, that'll be a -13. So we'll just do 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Right here. So this will just be, excuse me, -13.6. Well, it's not so bad. I shouldn't complain. You know, there's a price to be paid. Now, of course, y equal -4. So just using the focus. So we got 1, so 1, 2, 3, 4 down here. There's also with the SmartPen videos, there's extra stuff with this for my students that teach that don't attend class. So there's all kinds of extra resources with this. This is anything with analytic geometry, I love teaching. And then of course, infinite series and solving equations with analysis and all is always fun. So now we see here, if we draw the curve, we've got our 2 free points from the focal diameter. So we can just sketch this in. Right there. And here, here's our focus, -3, 6. And then of course the focal diameter is 20. So I just added that in, and there's your directrix. So again, the focal diameter gives it, you cut it in half and you just get a cheap way to get 2 extra points. And so that's not so bad. So again, the translation equations are the key. You don't want to guess. Basically, you look at the equation and say, okay, that's got 1 squared term. That's probably a parabola. So complete the square and then figure out the translation. That is here, you're looking for these 2 guys here. So you can figure out the h and the k. Here, the h is -3, the k is 1. And then you can go over here when you need to change equations. Because see, when we do the parabola and the hyperbola, we have the directrix and the asymptote. So we have to change the equations using these guys here, okay? But when we're getting the points, we have to use these guys. So we want the new coordinate system expressed in the old. So that's really important that you think about both of these. Now with the ellipse, we don't have any equations. We don't have a directrix. We don't have a hyperbola. So it's easier. So let's just go ahead and quickly set one up with the ellipse. Let's see here. I think I've got one. Yeah, we'll just quickly put that together. So the only thing that's remotely tricky about the conics is just the translation, but it's not hard. It's really simple. You just remember, get your note cards and make your nice notes, as they say. So now let's look at this one, 4x squared. So what I wanted to do was just say, give you examples where you would actually need to use this. Not just making something up, but then once you have a situation where it makes sense, then you can say, oh, okay, this is what we did. And so again, we have x prime equals x minus h, y prime equals x minus k, if and only if x equals x prime plus h, y equals y prime plus k. And this is like writing down c squared equals a squared minus b squared for the ellipse. Don't do it in your head, write it down so you can visually see the connection with the algebra to avoid carelessness. It's hard enough to write things down technically, so do yourself. If you write things down, then you can always check yourself. I can always figure out a mistake as long as I'm writing things down. When I stop and I get sloppy, that's when the mistakes ensue. So it's just what you do. So now when you look at this, you can at least see that you've got two square terms and they both have positive coefficients. So you think this is an ellipse. Maybe it's degenerate, but you think this is an ellipse. So let's complete the square in the x and the y. So we have 4x squared minus 16x, that together. And then we have plus 25y squared. And then we have what? Plus 250y. And so we've taken care of all of these. And then we've got this, just take this over, negative 541. So now let's go ahead and factor here. So we want to make the mnemonic. So we have x squared minus 4x. And then we have plus 25. And we have y squared plus a 10y. So again, just the factoring is what we normally do. That's the easy part. Then we complete the square. So half of negative 4 is negative 2. We square it, we get a 4. So plus 4 minus 4. Half of 10 is 5. Square it, we get a 25 minus a 25. So this gives us a 4 times an x minus 2 quantity squared. And let me go ahead and write the extra. So we get minus a 16 when we got the riffraff here. And then we get plus 25. So I'll just say, put that in parentheses. And then 25 times y plus 5 quantity squared. Then we got a 25 times a 25. So that's plus a negative 625. How interesting. Which equals negative 541. So now we have 4 times x minus 2 quantity squared plus 25 times y plus 5 quantity squared. And so now when we do this, if you notice here, we get a 1 and a 4. So we get a negative 641. How useful. We get a negative 641. So we add to both sides. That's a 641 minus a 541. So Dr. Stewart was good to us. That's 100, right? And lo and behold, that's what 4 times 25. So now we can divide. So divide by 4 times 25. So that'll give us an x minus 2. The 4 is absorbed, giving us a 25. And here the 25 is absorbed, giving us a 4. So now when you look at this, we can write down all the particulars, and then you can make a sketch. The ellipse is a walk in the park compared to the parabola and the hyperbola. So now we have a squared equals 25. We have b squared equals 4. So c squared equals 25. A squared minus b squared minus 4, which is 21. So a equals 5, b equals 2, and c equals the square root of 21. Now, as we look here and check this out, we have h. So we got the new center, so to speak. We have h equals 2, and comparing this, k is negative 5. So this gives us x prime equals x minus 2, y prime equals, I keep doing that. Sorry, kids. That's a y there. Y, in this case, minus a negative plus 5. How funny. And that's what I tell you. I said, if you write everything down, you can go back and figure out where the problem is. And I practice what I preach. I mean, I'm not too proud. It doesn't matter how smart you are, you're still human. So now we're thinking, okay, well, let's write everything down. The center, or the new center, let's do this. I think this was the notation that I used before. So the old center, or the new center in the new coordinate system, would just be this: center 2, -5. It's like the center of the circle, but it's not quite a circle. And then let's see, we need the vertices. So this is the larger denominator. So we have plus or minus 5, comma 0. So now we want to do, in this case, the coordinates with this. So we're going to have plus or minus 5 plus 2, and then 0 minus 5. So we have plus or minus 5 plus 2 using this, and then 0 plus k. K is -5. So 0 minus 5. So this gives us the plus or minus 5 plus 2, comma -5. So this will give us a B2. If we add, we get 7, -5. B1, if we have the subtraction, that gives us what? -3, -5. And now the foci, remember that's plus or minus square root 21, 0. Now use the, and here, let me get that a little bit closer. I don't need an extra equals. So we have prime, now unprimed. So we have plus or minus square root 21. Now we add the h plus the 2, and then we add the k, which is -5. So this gives us focus 2 will be square root 21 plus 2, -5. Focus 1, negative square root 21 plus 2 minus 5. Now, of course, the eccentricity, how simple, right? C over A, and that'll just be the square root of 21 over 5, which is the square root of 21 over 25. So the idea here is the translation just is a little extra busy work here based, and of course, like I said before, notice we don't have to use these guys because we don't have equations to translate. We only have to translate the actual points. That is, we have a new center. In this case, we have new vertices in the sense that they've been moved around. We have new foci in the sense that they've been moved around. So the key here, ladies and gentlemen, is look for the pattern of the conic, complete the square, figure out the h and k, write down your translation equations, change the new system into the old using this, and then change equations using this. So the key here, and this again, it's subtle, it's not very difficult, but if you pay attention to the transformation process here with the equations, then it's very straightforward. So in your web assignment, this section, they'll have something like this, and then they'll have a laundry list of things. And when it doesn't apply, you're going to do D and E for does not exist. If it does apply, you type it in and you follow the formatting. Again, very dry, not very interesting, but you need to know enough about conics so that when you see one, you can know that it's translated, know how to graph it or whatever, and know how to generate the new points of interest. So I hope that you've enjoyed this. I know, like I say, it's not as much pizzazz as the trigonometry. Trigonometry is just very elegant. This is just kind of busy work and not as fun, but very useful because you see the conics in physics, you see the conics in differential geometry, calculus, engineering, they're all over the place. And because of all of their reflective properties, we can't get away from them. So if you have some extra time, research the reflective properties of the conics, ladies and gentlemen. You will be absolutely fascinated. They are a marvelous set of objects that have been known for centuries, and we still to this day use their reflective properties. I mean, we are tied to the conics like we are tied to the calculus. So if I don't see you at the office hours today or tomorrow, good luck with your studying. Get your work done. Get your preparation for your test. Remember that you will submit your work, turn it in within an hour after you complete your WebAssign. And then once you get all of your work done with your math, you can take a break. I know you have other subjects, but I'm sure they're, well, maybe they're not as tough as this. I don't know. It depends. I think you all are just really busy, like Professor Ron. So thank you for your attendance today. Stay warm and have a good day. Bye, everyone.
Have a good day, sir.
Thanks, everyone.
Thank you.
Bye.